Hey everyone, so this is the elevator problem, and over on the side we will look at the notes. I'll include in the title here how far to skip in just to kind of see the notes portion, but really this is going to be kind of going over it in a conceptual way first without just all the wording and stuff, so you can kind of see how to think through what is actually going on here with the elevator. And so to start off, you go to the doctors, and first thing they do is they go, all right, we want to take your weight today, right? We want to measure what are you standing at? What are you tipping the scales at, right? And so the funny thing is you go in and you stand on the scale and you get, I don't know, let's say 84.7 kilograms. It's definitely a little on the heavy side. Well, what that does is it's actually not measuring the pull of gravity, the force of gravity down on you. What that's actually doing is that's measuring and kind of recording how much the scale has to push back up to fight that pull of gravity. So you see, you're sitting at rest, you're just kind of stationary, just kind of chilling there on the scale. And so you're at rest, and that means that there's no acceleration. You're not speeding upwards, you're not speeding up going downwards. Your acceleration is zero. You're like at rest. And so really the main thing, the most important thing here is that the scale measures the normal force, right? That's what the scale really does. So if I were to change this, I would say the scale measures the normal force. That's the most important thing. So if you're at rest or if you're moving at a constant velocity, meaning you're not speeding up in either direction, you're going to get your correct weight. But if you're accelerating, well, that means something funny is going to happen. So let's kind of look at the first one, which you've already talked about. If you're at rest or if you're moving up or down in an elevator at a constant speed, well, you're going to find that the scale shows your typical weight. And so what that really means is just that the size of the normal force matches the size of the force of gravity. Those two are the same size. So if I were to kind of draw this actually here, well, if my force of gravity is 2 lines tall going down, this one would have to be 2 lines tall going up. So they're actually the match, they're the same exact size. And so that's really because the normal force is matching the force of gravity because we have zero acceleration. So really, we get a big old zero on this side, and that means our net force is zero. Now, kind of thinking a little farther about this. Hopefully you've been in an elevator somewhere, and imagine you're at like a fancy hotel that has a really tall elevator, all right? And you're in at the bottom floor. And what you're going to do is you're going to begin at the bottom floor, you're going to go up to like the 100th floor, and then you're going to come all the way back down. So you're going to do a full trip, okay? And so thinking about that, if you get in at the bottom floor, then the first thing that's going to have to start happening is it's going to have to start going faster and faster. That's accelerating. The speed is increasing, whether it's in one direction or the other. So it's accelerating, and if you walk in the bottom floor, you'll be accelerating up. Okay. Now, gravity on Earth isn't changing when you get in an elevator, and if the elevator is going up or down or whatever, right? Gravity is the same, and so we get the same size for the force of gravity. So my force of gravity is still 2 lines kind of tall, and that's what I have right here. All right. So it's 2 lines tall, but now I'm accelerating up. That means that my acceleration, well, is up. That's what that really means, which means that my net force is also up. So if we think about that, if we're speeding up in that direction, well, the normal force and force of gravity can't match each other anymore. If they was matched, we'd have no acceleration. So this tells me then that my normal force must be greater in size than my force of gravity. Force of gravity hasn't changed. Gravity is the same everywhere on Earth. But now my normal force has actually gotten bigger. Okay? And so it's like now it's 1, 2, 3 lines tall. What that tells me then is that, hey, my scale has to push harder up on me. And so we see I have a little scale right here. So the scale has to push harder upwards on me. And so that means that, well, if the scale measures the normal force, well, the scale is going to make it look like I'm heavier. I'm going to appear, oops, I can spell, appear heavier. And now I'm going to appear heavier because the normal force is bigger than the force of gravity, and that results in this difference. Again, the net force is this like leftover force, and so the force of gravity kind of matches from here to here, and so we have this little extra leftover that is this green net force arrow, and so that net force is going up, so that means the acceleration is going to go up, and that's why we appear heavier. Now, the neat thing is this isn't just accelerating up. There's another circumstance that actually totally does also make you appear heavier. And we'll kind of think about, I want you just thinking about that one and what that might be. So now, we've looked at when you take off from the bottom floor and you're going faster and faster and faster, you're going to look heavier on the scale. And then the elevator is going to reach this constant speed and you'll actually show your typical weight. Now, on the way up, the last thing that happens is before you reach the top floor, the elevator has to start decelerating while it goes up. It's going slower and slower. It's going to slow down. So if we kind of think about that, the velocity is going, that's not up, the velocity is going up. But if it's going to start slowing down, that means there has to be a force pushing down on it that's kind of resisting it, right? Otherwise, it wouldn't be slowing down. It'd be going the same speed or going faster and faster. So that means that our acceleration has to be going down. Now, if our acceleration has to go down, that means that our net force must be aiming in the downward direction. And so to have a net force that's going in the downward direction, well, that means that gravity must be kind of winning out over my normal force. So in other words, the size of my normal force is less than the size of my force of gravity. Because again, my actual mass has not changed. And the force of gravity is just m times g. So my mass hasn't changed. Gravity has not changed on Earth. But my normal force absolutely must change. And so this tells me then that, hey, well, now my normal force is just going to be this big. And so if it's only like a little over a line tall, it's maybe like right there. There's my normal force. And so we can see that there is now between my force of gravity here and my normal force here, we do have a little leftover or difference in forces, which is aiming downwards. And that's what's going to slow me down, so decelerate me on the way up. And that's why you, in the end, appear lighter because the normal force, appear lighter. Because the normal force is what the scale shows, and if the normal force is now less than the force of gravity, you appear lighter. You actually do kind of feel lighter, and that's why if you jump at the very, like as you're reaching the top and the elevator starts to slow down, you jump up really, really high, right? You almost like smash the ceiling of the elevator because you appear and actually feel lighter, okay, which is kind of neat, kind of bizarre. So now there's another time that you feel lighter in the elevator though, and it's not just when you're decelerating on the way up, but also when you are accelerating on the way down. Think about it when you are at the very top and it hasn't started going down yet, but then you jump, right? And you again almost smash in the ceiling, right? Well, if it's accelerating down, that means, well, it's accelerating down. So the net force must be down. And so again, this normal force must be smaller than the force of gravity. We get the same result, whether you're decelerating up or accelerating down, which is kind of neat, right? And then this last one, well, we have accelerating down, we have accelerating up, we have decelerating up. This one must be decelerating down. And now if we think about that, as you're on the trip down, you don't want to smash in to the bottom of the floor of the hotel at all, right? Heck no, that's not fun. That sounds dangerous. That sounds like a lawsuit. So on the way down, what happens is the normal force increases and it starts resisting your motion. You're moving it with a downward velocity, but you need that velocity to become smaller and smaller and smaller and smaller in size. And so that means you must have a net force and acceleration that are pointing upwards. And that's why you appear heavier when you're decelerating on the way down. Okay, so that's kind of the thinking through. That's kind of the conceptual way going about it. And now, as far as the actual note portion, I want to go really quick through this because it's stuff we've already done it, but now I've kind of given you some number examples, all right? So scenario one is really just the elevator either not moving or it's the elevator moving at a constant velocity, because in both those cases, the acceleration is zero. So that means the net force is zero. And that means just that the normal force's size must match gravity's size. And so you get your kind of normal typical weight, right? The scale just shows their weight, which is kind of neat. And let's say for easy number's sake, they have a mass of 100 kilograms. Well, then their weight is mass times g. They're going to get a then weight of 980 kilograms. But that is also what the scale shows, because the scale shows that normal force, right? So the scale shows 980 for them, which is what their normal kind of weight at the doctors would be. So now if we look at the elevator accelerating up or decelerating on the way down, and let's say that there's an A value of 1 meter per second squared, okay? Because I want to give you some kind of samples with actually doing the math part here. So, well, we know that Newton's second law is the net force is mass times acceleration, and we know their mass is 100 kilograms, and now we know the acceleration. So we can figure out, well, what the heck is the net force? Well, if the acceleration is 1 meter per second squared and their mass is 100 kilograms, well, that means the net force is just this 100 newtons. So kind of neat, kind of easy, hopefully pretty kind of straightforward. All right, we can find the net force, poof. But now we also know that the net force, really kind of writing it out symbolically, is, well, the difference between this force and this one. And so instead of just writing the net force is ma, we're getting in this practice of writing the net force, well, it's the difference between the forces actually acting in this scenario. And so the neat thing is we already know this thing on the left side. It's 100 newtons, right? And we know the force of gravity. It's 980 up here, right? So since we know both of those, we can just kind of add this Fg over to this side, right? And then we just get that, hey, well, look in here, we can see that 100 newtons, because that's the net force, plus their force of gravity gives me the net force. So they do, in fact, appear heavier. The scale shows a heavier weight than normal. Kind of neat, right? And then the last scenario is the elevator is decelerating. So it's slowing down on the way up, or it's speeding up as it moves down. So now we're going to have an acceleration that is downwards, okay? So our acceleration is downwards, and that's why it has this negative symbol. And so since it's downwards, that means the net force must be downwards. And so if before the net force was positive 100 newtons because it was going up in the positive direction, well, now that net force just must be negative 100 newtons. So now, writing it again, we still have the same thing. The net force, or the normal force, is still up in the positive direction. So my kind of symbolic version of F net equals whatever's actually acting here, I still have the same thing as before, because the normal force is still going up in the positive direction. The force of gravity is still down in the negative. That's why I'm subtracting here. And since we now know the net force that we can kind of plug in right here, I've literally just gone and plugged in for it. I know their weight hasn't changed. Gravity on Earth has not changed. And so we're really just trying to find out, what does the scale read for them? Do they actually appear lighter if it's decelerating on the way up, or if it's accelerating on the way down? Yes, they do. They appear 100 newtons lighter than they normally do. So they actually do, in fact, appear lighter. And that is actually it for the notes.